The convergence of aging and obesity presents a compounded metabolic challenge, one marked by mitochondrial decline, insulin resistance, inflammation, and cellular waste accumulation. Both conditions share a key pathological hallmark: impaired autophagy. As cellular self-renewal processes deteriorate, tissues become increasingly unable to clear damaged organelles, dysfunctional proteins, and senescent cells. While NMN, nicotinamide mononucleotide, has attracted considerable attention for its ability to replenish NAD+ and reactivate autophagy through sirtuin and EMPK signaling, the therapeutic potential of combining NMN with other autophagy agonists such as spermidine offers an exciting frontier. Together, these compounds may create a synergistic metabolic intervention capable of reversing obesity-linked aging phenotypes while enhancing resilience and longevity. NMN primarily works by restoring intracellular NAD+, a coenzyme essential for the activity of sirtuins, particularly SIRT1 and SIRT3, which regulate mitochondrial biogenesis, DNA repair, and autophagic gene expression. NAD+ also modulates the EMPK pathway, a sensor of energy stress that promotes autophagosome formation and inhibits mTOR, the master autophagy suppressor. On the other hand, spermidine, a naturally occurring polyamine, induces autophagy independently of NAD+, acting via hypocyanation of EF5A, upregulation of autophagy-related genes, ATGs, and inhibition of acetyltransferases that suppress autophagic initiation. Unlike pharmacological mTOR inhibitors such as rapamycin, spermidine maintains mTOR-independent activation of autophagy, offering a complementary mechanism to NMN's energy-sensing pathway. Preclinical models of aging and obesity provide strong evidence that both NMN and spermidine independently reverse metabolic defects. NMN improves insulin sensitivity, hepatic mitochondrial respiration, and fat oxidation, while also attenuating inflammation in white adipose tissue. Spermidine, meanwhile, reduces ectopic fat accumulation, enhances mitochondrial structure, and extends lifespan in rodents, with effects highly dependent on functional autophagy machinery. The combined administration of NMN and spermidine, therefore, holds the potential for additive or even synergistic effects by targeting multiple nodes in the autophagy network while concurrently enhancing cellular energetics. Recent animal studies have begun to investigate this dual strategy. In aged, diet-induced obese mice, co-treatment with NMN and spermidine leads to significantly greater reductions in visceral fat mass, fasting glucose, and inflammatory cytokines than either compound alone. Liver histology reveals improved hepatic architecture, fewer lipid droplets, and increased expression of mitophagy markers such as PINK1 and LC3-2. Muscle tissue also shows enhanced mitochondrial density and reduced oxidative damage, reflecting a more youthful metabolic profile. These effects appear to be accompanied by increased circulating adiponectin and reduced leptin resistance, suggesting that systemic endocrine signaling is favorably reset when both NAD+ and autophagic flux are restored simultaneously. What makes the NMN-spermidine pairing particularly compelling is its impact on mitochondrial quality control. NMN boosts mitochondrial biogenesis through PGC-1A and SIRT1, but without efficient autophagic clearance, especially mitophagy, the buildup of defective mitochondria can still impair function. Spermidine, by activating autophagy at the level of autophagosome formation and lysosomal degradation, complements NMN's ability to generate new mitochondria by ensuring that the cellular environment is cleared of defective organelles. This mitochondrial turnover loop, biogenesis plus degradation, is essential to maintaining energy homeostasis in metabolically active tissues like liver, skeletal muscle, and brown adipose tissue. Beyond organelle recycling, the combination therapy may also act as a senesthetic strategy by suppressing the accumulation of senescent cells. Both NMN and spermidine reduce markers of cellular senescence in aged tissues, but via partially distinct pathways. NMN acts through sirtuin activation and mitochondrial restoration, reducing the cellular damage that drives senescence. Spermidine suppresses SASB production and promotes autophagic degradation of inflammasome components, limiting the inflammatory cascade that senescent cells provoke. This dual suppression of senescence and inflammation may translate into systemic improvements in insulin action, lipid metabolism, and even cognitive resilience, hallmarks of metabolic health span extension. Importantly, both NMN and Spermidine are orally bioavailable and well-tolerated in animal models and early human trials, with minimal toxicity reported at physiological doses. This enhances the feasibility of combined administration in aging populations. A few pilot clinical studies are underway examining their effects independently on metabolic markers and immune function, and it is likely that combination trials will follow in the near future. Given the safety profile and complementary modes of action, such dual interventions could serve as a cornerstone of multi-targeted aging therapies, especially for individuals with obesity or metabolic syndrome. Ultimately, combining NMN with autophagy activators like Spermidine offers a highly promising therapeutic synergy. It targets both the energy deficit and the waste accumulation that characterize aging-related obesity. By simultaneously enhancing NAD+ availability and autophagic clearance capacity, this pairing reboots the cellular renewal cycle that naturally declines with age. As research progresses, it may become increasingly clear that monotherapies are insufficient for tackling the complexity of aging metabolism, and that intelligent combinations like NMN plus Spermidine are better suited to restore balance across the full metabolic landscape.